Good morning friends, I am S. Hariharan, Assistant Professor, PG Department of Mathematics, KSR College of Arts and Science for Roman, Tirusangod. In this video, we are going to discuss about calculus of variation and integral equation one by one. So in this video, we are going to cover the following topics: introduction, functional, extremum of a functional, admissible functions, Euler's equation, another form of Euler's equation, Green's theorem, Barik-Strokon problem, maxima or minima of functionals one by one. So first of all, introduction. This chapter contains methods to obtain extremum of a given functional in one variable, several variable for functional involving higher derivatives and variational derivatives. Functional. What is meant by functional? A functional is a kind of function where the independent variable is itself a function. Thus, the domain of the functional is the set of functions. That is, in simple manner, we can say a function of function is called a functional. Extremum of a functional. We say that the functional j of y has an extremum for y equal to y if I of y minus I of y does not change sign in some neighborhood of the curve y equal to y of x, depending upon whether the functional are the elements of c of a comma b or d of a comma b. We define two kinds of extrema. Admissible functions. The set of functions satisfying the constraints of a given variational problem are called admissible functions of that variational problem. Euler's equation. Let I of y of x equal to integral x naught to x1 f of x comma y dash into dx be a functional defined on the set of functions y of x which have continuous first derivatives in x naught comma x1 and satisfy the boundary condition y of x naught equal to capital A and y of x1 equal to capital B. Then a necessary condition for I of y of x to have an extremum for a given function y of x is that y of x satisfy the equation dou f divided by dou y minus d by dx of dou f divided by dou y dash equal to 0, and the last equation it is called an Euler's equation. Another form of Euler's equation, that is, another form of Euler's equations are d by dx of f minus y dash into dou f by dou y dash minus dou f by dou x equal to 0, and fy minus fxy dash minus y dash into fy dash minus y double dash into fy dash square equal to 0, and the last one, when f equal to f of x comma y, then dou f by dou y equal to 0. These three equations are another form of Euler's equation. Then Green's theorem. Green's theorem states that double integral dou q divided by dou x minus dou p divided by dou y into dx into dy equal to integral p into dx plus q into dy, where d is boundary of the surface R and it is called Green's theorem. Then Barik-Strokon problem. Suppose P and Q are 2 points in the plane but not in the same vertical line. Imagine there is a thin flexible wire connecting these 2 points. Suppose P is above Q and we let a frictionless bed travel under gravity from P to Q. The Barik-Strokon problem or quickest descent problem is concerned with determining the path of the bed when it reaches the point Q in the least possible time. This is called Barik-Strokon problem, and this problem was first introduced by J. Bernoulli in the mid of 17th century and it was first solved by Sir Isaac Newton. Then maxima of functionals. A functional I of y of x is said to have maximum on a curve y equal to y naught of x if the value of the functional on any curve close to y equal to y naught of x is less than or equal to that of I of y naught of x. That is, del I equal to I of y of x minus I of y naught of x is less than or equal to 0, and this is called maxima of functionals. Minima of functionals. A functional I of y of x is said to have minimum on a curve y equal to y naught of x if the value of the functional on any curve close to y equal to y naught of x is greater than or equal to that of I of y naught of x. That is, del I equal to I of y of x minus I of y naught of x is greater than or equal to 0, and this is called minima of functionals. Thank you.